Hello everyone. Today I'll be covering the derivation of E is equal to mc². So I had done this derivation today. I was sitting on the dining and I just accidentally derived it. So I'll be sharing the derivation with you guys. So let's get into it. So for the derivation, we'll have to take the following case. Let's say you have a mass of m. It doesn't have to be a point mass, but you accelerate it with the force F so that it attains a velocity of v. So this is the initial and this is the final. So we can see that the work done by the mass is equal to its final energy minus its initial. We can see that its initial energy is 0. And what I mean by energy is its kinetic. And here we have some energy E. So the work done by the mass will be equal to E, which is the energy it will have after accelerating. So we can see that the work done by our force on the mass m is equal to the negative of the work by m, which is equal to the negative of its energy. Now we keep that in mind. So we can recall that a work done by a force is equal to the integral of the force with respect to the distance it's covered. Once we do that, we can expand using Newton's second law. F is equal to ma. It will be equal to the integral of mass into acceleration dx. Now we can write instantaneous acceleration as dv by dt. So we can rewrite it like m dv by dt dx, integral of m dv by dt. This is the work done by the force. Now we can modify dv by dt a bit. dv by dt can also be written as dv by dx into dx by dt. And if we input that, we get m into dv by dx into dx by dt into dx. So the integral of that. Now we can see that dx by dt, if you have noticed, will just be v at that instant. And you can see that dx here and dx here cancel out. So what you're left with is integral of mv dv. So now let's leave this aside for a moment and let's talk about relativistic mass. So according to Einstein's special theory of relativity, if you have a some mass m at rest, let's say, then you get it into motion with a velocity of v, then its mass actually changes. And what Einstein's equation tells us is that m dash is equal to m by gamma, where gamma is the root of 1 minus v² by c². Now this has been denoted by gamma because it appears very frequently in special relativity. So it becomes quite convenient to use gamma. Now if we input this, so you can notice that this m we are talking about is actually m dash, because we are talking about the mass during motion. So we can just input that. Now using the rules of integration, we can take out m and we can simplify root of 1 minus v² by c² as root of c² minus v² by c² using the LCM, which just becomes root c² minus v² by c. Now since this is in the denominator here, the c gets transposed up to the numerator. So it's written as m integral of c by root c square minus v square into v dv. Now this is again reminding you work done by the force on the mass. This c is the speed of light. I'm sorry, I didn't mention that earlier, where c is the speed of light, and it's approximately equal to 3 into 10 raised to 8 meters per second. Now c is a constant, so we take it out, is equal to mc into integral of v by root of c square minus v square dv. Now if we integrate this function, so to integrate this we can say y is equal to root of c square minus v square. So now let's take the derivative of y with respect to v, and we get it as minus v square into negative 2v. Now you can see the negative 2 and 2 cancel, and you're left with negative v by root c square minus v square is dy by dv. Now you can write negative dy as v by root c square minus v square, multiplying both sides by negative dv. And you can see that this term is exactly the same term that we have here. So now you can rewrite this entire term as negative mc into the integral of dy, which is basically y, because you can write integral of dy as integral of 1 with respect to y, which is just y. So therefore we get work done by the force is negative mc into y. And as you can see, y is c square minus v square. If we input that, we get negative mc into root of c square minus v square. That's the work done by the force. Now we need to relate this to the energy of the particle, which we have conveniently done here. Work done by the force on the mass is negative of the work done by the mass, which is negative of its energy. So we can write that work done by the force is equal to the negative of the energy of the particle mass. So if we input that, negative E is equal to negative mc root of c square minus v square. So the negatives cancel and you get E is equal to mc by root c square minus v square. Now this is a very important formula. Now you can see that if you have a stationary mass m moving with velocity 0, if we input that into our function, we get E is equal to mc root c square, which is basically E is equal to mc square. There you have it. Now there's a better version of this. Now this only applies for rest masses. That if you had a rest mass and converted it into energy, it will be equal to mc square. It's quite a huge value. It's used to calculate the energies given off during nuclear fission and fusion. So it's quite useful. Now, if you see, we can see that E is equal to mc by c square minus v square is actually the complete formula, which is less well known. Now, root of c square minus v square can also be written as, if you recall, gamma is equal to root of 1 minus v square by c square. You can see that it's root of c square minus v square by c square. So gamma is equal to root of c square minus v square by c. And therefore you can see this term, root of c square minus v square, is equal to gamma times the speed of light. Now if we input this back into our equation, we get another nice little equation. E is equal to gamma mc square. So there you have it, the derivation of mc square. E is equal to mc square and E is equal to gamma mc square. So yes, thank you for watching and bye bye.